So it so happens that a lot of systems that we want to construct may be unstable. For example, let's say we want to design a system and we want to know what is the optimal possible way of designing the system, right? So what if the optimal possible way of designing the system is not stable? We need to know that before we can say that, okay, I cannot implement this optimal system. So only when we know that it is unstable, we can declare that it is not implementable. So for this analysis where we need to analyze and say that it is possible or not possible, we need the notion of instability. We need to analyze unstable systems. So we'll see an example now where a very simple device, which is the ideal low pass filter, itself has a lot of impractical properties. So what is an ideal low pass filter? An ideal low pass filter is something which has a spectrum like a rectangular signal, right? So we'll say that there is a cutoff of some omega naught. So what are we saying here? So we are saying that if you feed in a signal and if the signal contains a frequency component which is above omega naught, then the system will drive that to 0. So it will cut off all the frequencies which are greater than omega naught, and anything less than that it will pass, and hence the low pass filter. So which means this is 1 for omega naught, for omega less than or equal to omega naught, and 0 everywhere else. So this is our ideal low pass filter. Now, is this invertible? Is this causal? Is this stable? The first thing, is it invertible? Clearly it is not invertible. Why? Because it is taking the value 0 for several frequency values. So clearly this is not invertible. So if I pass in any frequency which is greater than omega naught, it is all going to become 0. So I cannot know what was actually passed at the input. So clearly this is not an invertible system. Is this causal? Well, this is band limited. Just by looking at it, we can say because it is band limited, this is not causal. Okay. And is this stable? Well, we don't know if this is stable, but by using our property of duality, we can say that it is a Sinc function, and the Sinc function is one example where it is not absolutely integrable. So clearly this is also not stable. So we can see this from the inverse Fourier transform. So what is the inverse Fourier transform? The inverse Fourier transform is h of t 1 by 2 pi integral minus infinity to infinity h of j omega e power j omega t d omega. So this is just 1 between minus omega naught to plus omega naught, and this gives us 1 by 2 pi e power j omega t divided by j omega from omega naught to minus omega naught, which gives us 1 by pi omega e power j omega naught t minus e power minus j omega naught t divided by 2j, which is sine omega naught t divided by pi, there is a t here, divided by pi t. In other words, this is omega naught by pi times sine omega naught t divided by omega naught t, which is equal to omega naught pi of Sinc omega naught t by pi. Okay. So clearly we know that this signal is not causal because it exists even for negative values of time, and if you try to find the absolute integration, this is not going to be finite, and hence this is unstable. So the ideal low pass filter, the low pass filter is the simplest filter that you can ever construct, and the best possible low pass filter, the optimal ideal low pass filter, is not invertible. That is something we expected because we want certain frequencies to be cut off. So that is still okay. But it is not even causal because it seems to take in the future input, and it is not even stable. So an ideal low pass filter has so many problems, and we can know that it has so many problems only when we analyze. So we need to study about causality and stability and invertibility even when the systems are unstable and non-causal, because only then we can make this analysis and then say, okay, this system is actually not implementable. So now the ideal low pass filter is none of these practically feasible system. So then what is a practically feasible system? Then we approximate the spectrum to something of this form. We let it take values which are tending to infinity. So we let the spectrum exist from minus infinity to plus infinity. For a simple example, what if we let the spectrum to look like a sinc function? So if we let the spectrum look like a sinc function, then clearly it is going to let the lower frequencies have a higher gain and the higher frequencies have a smaller gain. So this is approximately a low pass filter. Clearly this is not the ideal low pass filter, but an approximate low pass filter. And in the time domain, what will we have? We will have a rect signal, which is the rectangular signal. So this now becomes stable, which is good. It is still not causal because it has non-zero values for negative values of time. So all we need to do now here is simply shift it to the right. So what if I can shift the impulse response to the right like this? This is 0 and this is some 1. Now my impulse response becomes stable and it also has become causal. Of course, it is not invertible, but that is not my worry because anyway I am not looking for an invertible system. So now I have come up with a way of ensuring causality and stability. So what does the corresponding spectrum look like? The spectrum looks exactly like this for the magnitude plot, because when you shift in time, what changes is only the phase. So now there is a phase plot which is different. Okay, so there is a phase change for these frequencies, but the magnitude is still the same, which is good because what happens here now, your filtering still remains as such. So the lower frequencies are having a higher gain and the higher frequencies are having a very small gain, which is as good as getting attenuated. So this is an approximate low pass filter where we have a stable filter, we have a causal filter. The only price that we are paying is that we are not getting an ideal. So if I want an ideal filter something like this, then I would approximate it the sinc function. This is one way of approximation, not necessarily the best way. So this is one way of approximating so that I'll get an implementable system. Okay, and this implementable system ensures that it is causal, it is stable. But the other problem that I have now is because I've shifted the impulse response in the time domain, I'll also get some extra phase. So if I send a signal cos omega t, which is present here, the output will be cos omega t plus some phi, plus some non-zero phase. That is because the phase response is not 0 anymore because of this shift. If I shift it by some t naught here, then we know that this spectrum now gets multiplied with e power j omega t naught. So let's say I shift it to the right, so there is a minus. So because of this, there is an additive phase for each of those frequencies. So that there is always a phase delay that is added to the frequencies when you filter. So this is a practical problem. So when you filter in real life, you always end up adding a phase delay, and this phase delay comes purely because you want a causal system. You can get rid of this phase delay in real life when you filter only when the system is non-causal. So all causal filtering systems will introduce a phase delay like this. So this is something we can understand only through this analysis. So we studied Fourier transforms. From Fourier transforms, we understood that whenever there is a time shift, there is a corresponding phase which is added to the spectrum. And that has helped us to understand that if you implement any filter in real life, you can never get the original signal without a phase shift. The original signal, whichever is inside the band of the filter, will always come at the output with a phase shift, and that is because the system has to be causal.